In the last lecture, we looked at some electronic fundamentals. Now we're going to look at alternating current circuits. Okay, so in the case of an AC voltage applied to a resistor, the problem is very simple because the current and voltage are in phase with one another. So the voltage changes as the peak voltage times sine of 2 pi ft. F is the frequency, t is time. The current follows exactly this pattern, but just divided by R from Ohm's law. And as we saw before, the power dissipated is just given by V RMS squared over R. But what about reactive components? In this elementary introduction, I'm not going to give you a full mathematical treatment of reactive components, although that is something that you will need to be familiar with for the higher classes of license. But let's look at the two reactive components. The capacitor, and the circuit symbol is shown here with an example of some capacitors in the picture, and the inductor, where the circuit symbol shown here and an example of the inductor shown to the right here. Broadly speaking, these things do what the symbols show they do. In other words, a capacitor will not pass a direct current. It's a gap in the circuit. It actually consists of two very closely spaced conductors separated by a dielectric. And we'll see in a minute that while it blocks DC, it will pass AC current and do so more readily the higher the frequency of the AC current. An inductor does the opposite. It passes DC, after all, it's just a piece of wire, but it blocks AC because by coiling the wire together, a dense magnetic field is created. And if you try and change the current through the inductor, one has to change the energy in this magnetic field, and that costs a lot of energy. So let's start off with capacitors. Here are some more pictures of capacitors. Capacitors are really very difficult to identify. I showed you a very nice simple resistor color code. In capacitors, my advice is always to stick what you see printed on the capacitor into Google and ask it. But a very common way of labeling capacitors is shown here, where the 683 means 68 times 10 cubed picofarads, or 68 nanofarads. Now, what is a farad? A farad is a fundamental unit of capacitance. The defining equation is that the charge stored on a capacitor is equal to the capacitance times the voltage. So the capacitance is the constant of proportionality between the voltage applied across a capacitor and the amount of charge stored on its plates. The charge storage occurs because the two plates are very close to one another. There's an intense electric field. And so the terminal that is connected to the source of positive charge attracts negative charges in the opposite plate. And then if you have no way of discharging the capacitance, that charge will just sit there. So a capacitance of 1 farad stores 1 coulomb at 1 volt. And then as you see in the example given here, that a more common value of capacitance would be some nanofarads. Below are the rules for adding capacitors in series and parallel. In parallel, the total charge just adds up, so the capacitance is the sum of the individual capacitors. In series, it's a bit more complicated. The total capacitance, 1 over the total capacitance, is 1 over the first capacitance plus 1 over the second capacitance. Now, a little bit of math here, but I can explain it qualitatively. We have the defining equation that Q equals CV. The current through a circuit containing a capacitor is the time change of Q. Remember, a current of 1 amp is 1 coulomb per second. In calculus terms, this is put as dq by dt, or if you just wish to think of this as the change of Q as a function of time, And then if we take the time derivative of the right-hand term, it's given by C dV dt. So what we see is if the voltage applied across a capacitor doesn't change with time, dV dt is 0, then I is 0. The capacitor blocks DC current. But as we increase the rate of change of voltage with time, in other words, as we go to higher frequencies, we increase the current through a given capacitor. Now, when you do the math, it turns out that when you are increasing the voltage on a capacitor up to the point where the sine wave reaches its maximum, the rate of change of voltage at the maximum of that sine wave is, of course, the smallest. So here you have the largest change with time, and here you have the smallest change with time. So at this point, the current is a maximum, and at this point, the current goes through 0. And what this means is that if you apply a sine wave, the current goes as a cosine wave. It is 90 degrees out of phase with the voltage. We say that current lags voltage by 90 degrees in a capacitor. Now, we can incorporate all of this by talking about a quantity that's like resistance. It has a unit of ohms, but the imaginary number I is used to encapsulate the fact that the current varies like a cosine while the voltage varies like a sine. Once again, you don't need to be familiar with this at the technician class license point, but you do need to know that the X means a reactance, and that means that current and voltage are not generally in phase. The reactance of the capacitance is given by 1 over omega C, where omega here is 2 pi F. Okay, what about inductors? According to Faraday's law, a change in magnetic flux through an inductor generates a potential difference across the terminals of the inductor, or in other words, the potential difference opposing the change of current is minus L times the rate of change of current, written here as di dt. So if you have an inductor of 1 Henry and you change the current through it by 1 amp per second, then a voltage of 1 volt will be generated across the terminal of the inductance. Alternately, we can define the Henry of inductance as that inductance which, for a current change of 1 volt per second, gives you an opposing voltage, minus sign there, of 1 volt. So the inductor tries to oppose the change of applied current. It therefore passes DC and blocks AC. Now, in an inductor, current leads voltage by 90 degrees. So once again, a reactive component, and the reactance in this case is given by omega L, where omega is 2 pi F times L. You'll often see two coupled inductors, and this is a very useful arrangement where the inductors share their magnetic field. So a change in current through one inductor causes a change in potential across the second inductor, and this is how a transformer works. With equal numbers of turns, they're still useful devices because they isolate one circuit from another, from a common ground. And of course, with different numbers of turns, they are the things that turn the voltage from the high voltage transmission lines into our useful 120 volts. Here is the inductive reactance worked out. You don't need to bother about the math, but as I said, the reactance is omega L. The so-called impedance, the complex form of reactance, is I omega L, where I is the square root of -1. Something you'll need for the more advanced levels of license, but not for the technician license. Now, let's take a look at an LR circuit or an LC circuit. There's a C missing from the caption in this slide, where we have an inductor and a capacitor in parallel. Now, we know that if we apply a low frequency voltage V in, that the inductor will short it. Certainly as it goes towards DC, that coil will just become a piece of wire, letting the current go straight to ground. On the other hand, if we apply a very high frequency, the capacitor now becomes like a piece of wire, and the current through the capacitance will be very high because the VDT is very high. So there is a magic point where the L and C both have some value of reactance other than 0, and just exactly cancel out one another. That happens when the reactance of the capacitance equals the reactance of the inductance. In other words, 1 over omega C equals omega L. And then if we solve that for the frequency at which this happens, we get this result, that the resonant frequency of this circuit is 1 over 2 pi times the square root of 1 over LC. Resonant circuits occur all over the place in radio electronics. Let's take a look at some real resonant circuits. So here's a resonant circuit I get the students to make in my electronics class. And so here are the values of components they use: 0.1 microfarads, 100 millihenries for L. There happens to be a 10 kilo ohm resistor there. And on the right, you see a plot of the voltage V out as a function of frequency. And you'll see that just above 10 cubed, there is a very sharp peak in output voltage, and it's close to 0 everywhere else. The formula we just had, that the resonant frequency is 1 over 2 pi 1 over the square root of LC, is 1 over 2 pi times 1 over 10 to the 8th. So that is 10 to the minus 8, rather. The minus is hidden under the bar there. So the 1 over 10 to the minus 8 is 10 to the 8th. The square root of 10 to the 8th is 10 to the 4th. 10 to the 4th times 1 over 2 pi is 10 to the 4th times about a 6th. And that turns out to be about 1.6 kilohertz frequency. And that's exactly what you see for the resonance. Okay, we dealt with reactive components very briefly. So next up, radio waves and propagation.